Namaste. We are towards the end of chapter Work, Energy and Power, and the only thing that is remaining is power. So today we will see what is power, what is its significance, and how numericals are solved from this topic. So let's be started.
What is power? Generally, we have more interest in knowing not only about the work, but what is the power, the rate at which this work is done. Like if we consider an example that a person is physically fit. So if he is fit, then he not only can climb 4 floors of a building, he can climb them fast. So this is power. Power is defined as the time rate at which work is done or energy is transferred. If we write mathematically, then power can be written as rate of doing work. So it has to be work upon time. This kind of power is average, where we are interested in the whole work done and the total time taken. But as you know, for all the physical quantities, we define its average and then its instantaneous value. So its instantaneous value will be, if we write the instantaneous power, it has to be, then we have to consider a very small amount of work done in a very small time. So it can be written as dW upon dt. This is how power can be written. If we are interested in its vectorial representation, see, power itself is not a vector, but as work can be expressed as dot product of two vector terms, so as the power. So power, if we write in vector form, it can be written as dW can be written as F dot dr upon dt. So from here we will get instantaneous power to be equal to F dot V. Now we have 1 and 2. Two definitions, mathematical definitions for power. We will use any whatever is required in the given situation. If in a numerical velocity is given, force is given, then we will need F dot V, and if work done is given there, then we have to write work done upon time. So this is how power is written. There can be one more mathematical definition to express power, because as we know that work done can be written as net change in kinetic energy. So this can be written as delta K upon T as well, that is net change in kinetic energy upon time. And in instantaneous form, it can be written as dk upon dt. Now we have various representation of power. Either it can be written as net work done upon net time, or dw by dt, or vectorially F dot V, or change in kinetic energy upon the whole time, or rate of change of kinetic energy with respect to time. These are all the ways in which we can represent power. Now come to its unit. As it is work upon time, so an obvious unit is joule per second, that is known as watt. But one very popular, because 1 watt is a very small quantity, very small power. So generally in convention, one more unit is there which is very much in use, that is called horsepower. And 1 HP is written as 746 watt. So this another unit is there for power, which is very common. Now here I have taken one example so that how power can be calculated is clear to you. An elevator can carry a maximum load of 1800 kg. This 1800 is the total load for elevator plus the passengers. The elevator is moving up with a constant speed of 2 meter per second. V is given as 2 meter per second. And the frictional force opposing the motion is 4000 Newton. Here friction is there. It has a constant value of force, that is 4000 Newton. What is the minimum power delivered by the motor to the elevator? Now here you have to think which formula should be used. As you can see, force is given there, velocity is given there. So which one should be used? It has to be F dot V. But it is asking for the net power developed, that is power developed by the motor. So of course it must include the whole force. Now what is the force? Total force acting has to be equal to mg plus F, because as the elevator is moving up, it has to do a work against gravity and against friction. So I have added the two forces which are acting in downward directions, that is mg plus F, and this value will be equal to, if we numerically solve the values, it will be 22,000 Newton. This is the total force required to be developed by the motor. So what should be power then? Power has to be equal to F dot V. As we know, this force has to be in upward direction and velocity also is in upward direction. So total power will be equal to 22,000 multiplied with 2. That is equal to 44,000 watt. If we write in horsepower, because that is very common unit, so it can be written as 59 horsepower. This is how a simple calculation is made with the help of formula P is equal to F dot V. Now we have to consider some of the cases in which motion along vertical circle is to be analyzed. Now why is it studied differently? Why is it studied separately? Because already we have studied circular motion, but for vertical circle always you have to write work energy conservation also. That is why it is included in chapter work energy and power. So while solving a question, if it comes from vertical circle, then see what equations are to be written. Here I am considering that one vehicle is moving against this circular track having radius r. This vehicle has mass m. Now if it goes from here to here, and if its original speed is given as u, and we have to calculate what should be its speed when it is at the topmost point, then how would we calculate it? See, we have to first write energy conservation between this lowermost position and the topmost position. So what will be the equation? Half mu square should be equal to, at the topmost point, kinetic energy has come to half mv square plus the potential energy it has gained. Now while writing potential energy, I have taken reference at the lowest position, so that at the lowest position potential energy is 0, and at highest position it will be equal to mg. The total height is 2r, so this is mg multiplied with 2r, and then we can write this v square will be equal to u square minus 4gr, and v is equal to under root u square minus 4gr. Now if it asks for the normal reaction provided by circular track at this topmost point, then we have to write one more equation that will be equal to, because at this position downward force has to be equal to n plus mg. So we can write n plus mg is equal to mv square by r, as we know that this is the required centripetal force as the vehicle is moving in vertical circle, and from here we can get value of n as well. It will be equal to mv square by r minus mg. Now you can substitute value of v from this equation number 1 to equation number 2 and get value of normal reaction. This is just to illustrate you so that how the questions are solved, how the equations are written when situation is of a motion along a vertical circle. We have to write two equations. One will be that of energy conservation and other has to be the force equation, that is F is equal to ma. Of course, since it is a circular motion, that a mostly has to be centripetal acceleration if it is a uniform circular motion. So we will remember these 2 points while solving a question in which there is vertical circular motion involved. I have taken one example also in this session. Let us consider one illustration. In the track shown in figure, section AB is a quadrant of a circle of 1 meter radius. A block is released at A and slides without friction until it reaches B. After B, it moves on a rough horizontal floor. This portion B to D is rough and comes to rest at distance 3 meters from B. What is the coefficient of friction between floor and body? From energy conservation we can write, when the block has reached to point B, From the point where it has been started, which is point A, mgl, that is the loss in potential energy, to be equal to gain in kinetic energy. So if the speed at B is u, we can write kinetic energy at B to be half mu square. On solving this, we will get u square to be equal to 2g. Now it has come to rest. So for the irregular, this path, that is the rough path, we can write v square to be equal to u square minus 2as. And on putting the value u square, we had got 2g. So it is 2g minus 2a. The distance travelled is 3 meter from here. So it is 3. And the final velocity is 0. On solving this, we will get a to be equal to g by 3. And so we can write that the frictional force will be mu mg. And thus a has to be equal to mu k into g. So mu k will be having value. It is g by 3 upon g. G got cancelled, that is 1 by 3, which is our option number A. As you can see, this is the example here, which includes both the part, that is motion along a vertical circle, and potential energy stored in a spring. The question says, the figure shows a small ball of mass 0.1 kg placed on a smooth plane surface OA, which acquires a semicircular shape ABC. This ABC is semicircular, having radius of 2 meter. This is value of R given. Mass of this is given, which is equal to 0.1 kg. The ball just touches a light spring of stiffness. K is also provided. It is equal to 1000 Newton per meter. The ball is pushed to the left so as to compress the spring by a distance x and released. This ball then starts moving towards the circular track. Now we have to find a number of things. So let us start with the first one. In first part, it is asking find the minimum work done by external agent to push the ball to the left through 50 centimeter. Okay. So let's start solving. When work done by external force to push the ball against spring is minimum, there must be no kinetic energy associated with the ball, because it is asking for the minimum force. So of course it cannot impart it the kinetic energy, and we can write work done is responsible only for potential energy. So for first part, we can write this W to be equal to half kx square. This is the minimum work required, and that will be equal to, if we substitute the numerical values, it will be half into 1000, and as it is pushed by 50 centimeter, so we have to write 50 upon 100 square of this, which is equal to 125 joule. So this is the minimum amount of work asked. This is our first part completed. In next part, it is asking if the ball is pushed to the left by 5 centimeter. Now it has been pushed by 5 centimeter only and released. Calculate, again two things are to be calculated. Normal force on ball just after crossing A. It has to be here at the point A, normal force, and then maximum angle covered on the circular track before it comes to rest. Okay, let's do this also. As the ball is leaving the spring, it will be moving towards right with a speed v. Now we can write from energy conservation, because potential energy will be converted into kinetic energy. So we can write half mv square to be equal to half kx square. From here we got v is equal to x root under k by m. This time it has been pushed only by 5 centimeter. So if we substitute these values, the v velocity will come out to be 5 meter per second. This is the velocity which the ball will be having when it leaves contact with the spring. Now for first part, if it crosses A, its path becomes circular and it will start experiencing a centripetal acceleration. As we all know, centripetal acceleration has to be equal to v square by r. So at this point A, if we write what forces are there, normal has to be in upward direction, mg has to be in downward direction. I am writing for point A. and then we can write n minus mg to be equal to mv square by r. On substituting the values, this normal force will be equal to 2.25 Newton. This is the force exerted by track when it reaches the point A. Now we have to solve its second part as well. So for second part, it is asking for what maximum angle it will curve before coming to rest. Let us consider that it has come to this point, which is at a height h with respect to the horizontal surface, and then it has come to rest. This position, let it be theta. Now at the point A, velocity already we are having, that is equal to v. So let us now solve this situation. We can write energy conservation between point A. Let this point be A dash. So we can write between A and A dash, mgh is equal to half mv square. As it has stopped at A dash, so no kinetic energy will be there at A dash. From here we will get h to be equal to, if you substitute numerically the values, that will be v square by 2g. It is equal to 1.25 meter. This is value of h. Now as you can see from the triangle here, let us draw a normal at this O being the center. We can write ON to be equal to r cos theta, and that should be equal to r minus h. Now we have value of h, we have value of r, so of course we can calculate value of theta. From here it can be written as r is given 2 meter. So this is 2 cos theta is equal to 2 minus 1.25. That is cos theta is equal to 0.75 upon 2, which is 3 by 8. So this is the angle made with vertical when it has speed 0. Theta has come equal to cos inverse 3 by 8. With this, now second part is also complete. Next is part C. What is the minimum distance by which the ball should be pushed to the left and released so that it reaches up to C? You can see here that C is the highest point. Now I am solving C. Let us consider that spring has been compressed by x. So what energy it will be having? Half kx square. Now since it has to reach point C, so just after leaving the contact, what speed it will be having? If we write half kx square to be equal to half mv square, where v is the speed at the point when it just leaves contact with the spring, we will get v to be equal to x root under k by m. This is our equation number 1. Now to complete the circular motion, minimum speed at A should be equal to, this is the minimum speed required at A, that has to be equal to root under 5gr. This we can get from energy conservation and centripetal force equation. So then we can substitute value of VA here, that was equal to x root under k by m we had obtained in our equation number 1. It should be equal to root under 5gr. Let this be equation 2. Now on solving we will get x to be equal to 0.1 meter. So the spring should be compressed by 0.1 meter at least, so that it can reach up to the maximum height, which is the point C. With this our C part is also complete. The last one is, if the ball is pushed to left by 0.7 of this x minimum we have just calculated in part C, then calculate reaction force between ball and track at B. B you can see here. Also the maximum height attained by the ball above horizontal surface. Okay, so let us see. When spring is compressed by 0.7 of, this is the x minimum we had got. So this time compression is, we have to consider x to be equal to 0.7 into 0.1, that is equal to 0.07 meter. The speed acquired by the ball then can be calculated from the formula, it is given here above. So it can be written, this one I am using, it will be equal to x under root k by m. On substituting the values, it will come out to be 7 meter per second. Now in its first part it is saying as the ball reaches B, its speed let that be equal to B. This is the point B here, and if speed at this point is VB. Now what conditions will be there? Of course normal has to be in this direction towards the center, and mg will be in vertically downward direction. So then we can write from energy conservation, half mv square should be equal to half mvb square plus mgr, which gives vb is equal to root under v square minus 2gr, and on substituting the numerical values it will come out to be 3 meter per second. If we write force equation at this point, then AC will be equal to centripetal acceleration will be equal to VB square by R, and this value comes out to be 9 by 2 meter per second square. So we can write N to be equal to mVB square by R, that is equal to 0.45 Newton. Now in the last part we have to see at what maximum height it will reach. So let us draw again that circular part. This is our point A, it is B here, and I am considering that till this point it has reached. Let that point be D. If at this position, at the maximum height when it has reached, it is making angle theta with the upper vertical. So now as the speed at lowest part is less than what is required to complete the circular track and reach C, the ball will leave the track before it reaches C. Of course it will leave. So I am considering that it is leaving contact at D itself. Now height at D, if you write that h has to be equal to r plus r cos theta, which can be written as r1 plus cos theta. And now by conservation of mechanical energy we can write half mv square is equal to half m speed. If at D it is equal to Vd, then half mvd square plus mgr 1 plus cos theta. Also we have to write fbd at D, and since it is leaving contact at D, then this normal has to be 0. So we will write mg cos theta only should be equal to mvd square upon r. If n is also there, then we would have written n plus mg cos theta, but as n has become 0 at this point, so we have to write only mg cos theta to be equal to centripetal force. From here we will get vd square is equal to gr cos theta. Let this be our equation number 1, this is our equation number 2. Then from these two equations 1 and 2 we can write half mv square is equal to mg r cos theta upon 2 plus mgr 1 plus cos theta. V square minus 2gr is equal to 3gr cos theta. From here we got value of cos theta to be equal to v square minus 2gr upon 3gr. Numerically, if we substitute all the values, then it will come out to be 3 by 20. And then h can be written as r 1 plus 3 by 20, which is equal to 2.3 meter. So till 2.3 meter it will continue moving on the track, and after that it will lose contact with the track. Now from point D, as it has lost contact with the track, it will start moving in a parabolic path, which will be like a projectile motion. So this is only under action of gravity, and this will point onward. It will rise up to further height, that can be h, and then we can write h to be equal to vd square sine square theta upon 2g. You can recall this equation, it is from projectile motion, the formula we used for maximum height. So this is, now it is starting its motion with initial speed Vd. So in place of V naught I have written Vd. Now if we substitute these values, that will be equal to 1173 upon 8000 meter. but this height is above the point where it had lost contact with the track. So the total height has to be equal to, we have to add the lower height h also. So total height we can write above horizontal level to be equal to h plus h, and this value will come out to be 2.45 meter, which is our final answer. This is the maximum height to which the particle will move, but not on the track. It will lose contact with the track and then will start following a parabolic path. I hope you all understood the concepts I have written while solving the numerical. And see, this is a long question, but each part can be made as a separate question. So just solve all the parts and then you can solve a number of things independently. With this, our today's session is complete. In next session, I will come up with a number of questions. Those will be the previously asked questions in your competition. So let us be prepared for that. Bye.